Hi, my name is Aidan Fitzpatrick, and I'm a graduate student at Stanford University. Today I will be presenting on our work entitled Spatial Reconstruction of Soil Moisture Content using Non-Contact Thermoacoustic Imaging. In an increasingly connected world, smart farms and intelligent land management could help to improve agricultural practices and allow for efficient resource usage. To achieve this concept, sensing technologies need to be developed, including those that can sense below-ground features such as the soil moisture. In addition to efficient irrigation scheduling, knowledge of soil moisture can be used to optimize soil health. As depicted here, soil moisture is an important parameter that impacts vital properties of the soil, including its chemical and biological composition. The most prevalent approaches today for measuring soil moisture are point-based sensors. However, they are all invasive, requiring a probe or sensor to be inserted into the ground. This not only limits spatial coverage, but also can corrupt the measurement environment itself. On the other end of the spectrum, remote sensing approaches have large spatial coverage but provide limited information about soil moisture profiles with depth. In addition, these approaches suffer from low temporal sampling. There is a lack of technologies that can provide field-scale soil moisture profiles with depth information and over regular intervals of time. In our work, we propose a novel technology that has the potential to overcome these gaps, reconstructing soil moisture profiles with depth while being completely non-invasive. This is done using a modality called thermoacoustics, wherein microwaves are absorbed by underground objects, such as root structures, causing thermal expansion and generation of sound waves that can be detected by high-sensitivity, airborne capacitive micromachined ultrasound transducers, or CMUTs. The propagation of the sound waves, most importantly the speed of sound in the soil, is dependent on the soil water content. While the absolute value of the speed of sound in soil varies with soil type, previous work has demonstrated a strong and repeatable dependence of the speed of sound to the soil water content. Thus, in this work, we focus on the reconstruction of a speed of sound profile as a proxy for measuring soil moisture content. To solve for the spatial distribution of the speed of sound in the soil, we first need to formulate a tractable problem. Let's take a look at these two graphics. First, if the speed of sound in a medium is uniform, the time it takes an acoustic wave to propagate from a transmitter to a receiver, or the time of flight, can be calculated as the time equals the distance over the speed of sound. On the other hand, if the speed of sound varies spatially, the time of flight relationship is not quite as simple. The time can be found by integrating 1 over the speed of sound along the acoustic wave propagation path. To further develop our problem, let's first discretize the equation found on the previous slide as a matrix multiplication where t is the time of flight, s is 1 over the speed of sound, also known as the slowness distribution, and h encodes the propagation path of shortest traversal time from the source to the receiver. For clarity, let's take a look at a simple example which contains 3 transmitters and 3 receivers. First, we discretize the domain of interest into x lateral voxels and z depth voxels. The slowness distribution is defined at each voxel and vectorized into a vector of size xz by 1. Next, we can see that there are 9 combinations of transmitters and receivers, so the time of flight vector t will be of size 9 by 1, containing the propagation times from each transmitter to each receiver. H encodes the voxels that are intersected by the propagation paths from each transmitter to each receiver. Therefore, H is of size 9 by xz, where each row of H encodes a single propagation path through the slowness distribution. An important thing to note is that due to refraction, the propagation path is not a simple straight path, but rather it is dependent on the slowness distribution. This dependence can be captured in our matrix multiplication. The desired unknown in this equation is the slowness distribution S. To solve for the slowness distribution, we can approach this inverse problem using least squares methods. Now that we have an idea of the general problem formulation, let's determine how we can apply these ideas to our application. A high-level look at the algorithm we will apply is noted here. First, we must acquire empirical time of flight of acoustic propagation paths through the medium of interest, in this case, the soil. Next, we must derive the forward matrix H. Finally, we can solve for the slowness distribution using least squares methods. These ideas and concepts have been previously used to map the distribution of the speed of sound in a medium, particularly in medical imaging using ultrasound tomography. In this application, a common approach for finding the empirical time of flights is to surround the medium of interest with an annular array of transducers. Each of these transducers can be operated as a transmitter or a receiver so that a single transducer can fire a pulse, and the remainder of the transducers can receive this pulse to determine a time of flight from the transmitter to each receiver. This is repeated for each transducer, acting as a transmitter, in order to increase the number of measurements and ensure a well-posed inverse problem. In our application, it is not feasible to transmit an ultrasound wave through the soil. Instead, we propose to make use of the thermoacoustic effect, where we can excite below-ground objects to act as in-soil transmitters. When these below-ground objects are excited by microwave energy, they all fire simultaneously, making it infeasible to delineate the time of flight from each of these underground sources to each receiver. Instead, we extract the empirical time of flights from the measurement data using the coherence factor formalism. The coherence factor concept is frequently used in ultrasound imaging, and qualitatively speaking, the coherence factor at the source pixel is maximized when the source is in focus. To explain this with more clarity, let's focus on the below graphics. We can sweep over uniform speed of sound values for the soil, reconstructing a coherence factor image using the above formula for each assumed uniform speed of sound. For each reconstructed coherence factor image, some sources are reconstructed in focus while others are not. The sources that are in focus have high coherence factor values since the measurement data is coherent across receiver array elements for the chosen uniform speed of sound in soil. In these graphics, for the specific speed of sound value of 565 meters per second, we can see that the coherence factor for this source is high. Therefore, we can assume that the average speed of sound of the soil above this point is 565 meters per second. This average speed assumption is valid as long as the lateral variation of the speed of sound is minimal in the true distribution. Using this average speed, we can calculate the empirical time of flight of an acoustic wave from this source to each receiver. This is repeated for each source in the soil using the speed of sound that maximizes the coherence factor for that given source. Now that we have extracted time of flights from the thermoacoustic measurement data, we must derive the forward matrix H before we can solve for the slowness distribution. A challenge that we encounter is that the matrix H depends on the slowness distribution, which we have no prior knowledge of. For the time being, let's derive the forward matrix H using a guess of the speed of sound distribution, and we will later circle back to this assumption. To refresh, the matrix H encodes the propagation paths from each below-ground source to each receiver in air. As mentioned, we need to know the speed of sound distribution in order to find the propagation paths. First, we guess the soil as an arbitrary but reasonable uniform value for the speed of sound. We then use a technique known as the fast marching method to solve the O'Connell equation, which I won't cover in detail here. On a high level, the fast marching method solves for the time of flight from any point in space to another point in space, taking refraction into consideration. Using the fast marching method, time of flight maps can be generated for each receiver. Each map, here we show two examples, contains pixel values that store the time of flight from that pixel in space to the receiver location. These fast marching method generated time of flight maps can be used to find the propagation paths from the sources to the receivers using a gradient descent ray tracing algorithm. While this map here is for a single receiver and shows the gradient descent ray trace for a single source receiver pair, this can be repeated for all sources in this map and then for all sources in each receiver-specific time of flight map. Each row of the forward matrix H encodes the pixels along a single acoustic path, as shown here. Therefore, if the domain is discretized into X lateral pixels and Z depth pixels, and there are M sources and N receivers, the matrix H is of size Mn, the number of source-receiver combinations, by Xz, the total number of pixels in the slowness distribution. Now that we have solved for the forward matrix, we can use least squares methods to solve for the slowness distribution. As seen in the figure, which shows all of the acoustic paths encoded in the forward matrix H, there are some pixels in the domain that are not intersected by even a single path. This means that the inverse problem is rather ill-posed. To combat this, we introduce a total variation regularizer, which penalizes reconstructed slowness distributions that have high gradients. This is a fair assumption since we expect the speed of sound in soil to vary rather slowly as a function of space. While this regularizer helps to make the problem better posed, it does complicate the reconstruction. The L1 norm is not differentiable and thus prohibits direct inverse filtering methods to solving least squares problems. Instead, we use the alternating direction method of multipliers, or ADMM, to solve this problem. After a number of ADMM iterations, an updated slowness distribution is found. If we stop here, however, the result will not be great due to the fact that the forward matrix H was constructed assuming a uniform soil sound speed distribution. Instead, we can feed back the found slowness distribution to rederive the forward matrix and repeat the process. This is looped over until the slowness distribution converges. Finally, we demonstrate the efficacy of our algorithm in simulation using K-Wave, a MATLAB toolbox. In the simulation setup, the receivers are modeled using a characterized model of our CMUTs. We first show a simulation that assumed a monotonically increasing speed of sound with depth. The approach is able to reconstruct the speed of sound distribution with an RMS error of only 9.7 meters per second. Among many other simulations that have demonstrated the efficacy of our algorithm, we also show here a non-monotonic distribution where the speed of sound first increases with depth and then subsequently decreases. The approach is able to reconstruct the distribution with 10 meters per second error. In this work, we demonstrated a non-contact thermoacoustic approach for mapping the speed of sound distribution, which is known to be highly correlated with the soil moisture content. While here we assume discrete points for the in-soil thermoacoustic sources, future work will exploit inherent soil heterogeneity or subsurface structures such as roots. With that, the proposed system could be used to sense soil moisture non-invasively on a field scale. Thank you for your attention, and we're happy to answer any questions.